All right, I think I'll get started. Okay, lots of people. So, hi guys, thank you for coming up to my talk. I'm Abhiroop, and this is my Twitter handle. And just make sure you're in the right talk, Vectorization in Haskell. And the work that I'm presenting is essentially, it was my master's thesis. So most all of this work, some part of it was also attached with the Google Summer of Code. I was working on the GHC compiler and making sure it supports vectorization, whatever that is. I'll explain it in the talk. This talk is aimed for all levels, and I want to make sure that the slides are self-contained. So please do ask me any doubts. If any questions you do have, stop me. So without any further ado, this was the title of my presentation. This is the title of my thesis. It's named after a very famous paper that was presented in PLDI. It was called Exploiting Super Word Level Parallelism. So we are going to be talking about super word level parallelism in the Glasgow Haskell compiler. So we all know GHC. So what exactly is super word level parallelism? So I will try to explain what that is, what form of parallelism, what form of parallel computing that is, and how I've integrated it into GHC, and how you as a Haskell programmer can utilize that. So almost all parallel programming talks generally start with saying that Moore's law is over. We should look for multi-core processors. Multi-core processors are coming in, which is absolutely correct. But I am not going to be talking about that line of parallel computing. It's the other thing. So to understand that, so let us see, these are the types of parallel machines. So this is from a paper in 1966. This is known as the Flynn's architecture, Flynn's taxonomy. And he defined 4 classes of machine. So on the x-axis, you can see the instruction stream, and on the y-axis is the data stream. And these are the classes of machine based on the instruction and the data parallelism. So what we are interested is in the bottom left portion, which is single instruction, multiple data. So the name kind of implies there is a single instruction, and that instruction is being applied on multiple pieces of data at the same time. So I explain that visually. So I hope that's visible at the back. So as you can see, these are normal scalar operation, where there is each addition operation is being operated on a pair of operands. But what happens in a vector model on a vector processor is that you have a single addition operation, and it will operate on 2, 4, 8, 16, or depending on the architecture, that many levels of data. So there are arithmetic operations, logical operations, shuffles, and number of other operations. But this is the main gist, that a single operation will operate parallelly on 4 pieces of data. So this is a little bit history of this. Historically, Cray 1 was the first supercomputer. I think it came out in the 1970s, which actually started following this design. In fact, all GPUs are also based on this design, where they have an increased number of arithmetic logic units, and a single instruction can parallelly operate on all of those data. For normal machines, this is the history. So surprisingly, this was existing since 1999. Actually, it's before that. There is an MMX set of instruction. So SSE stands for Streaming SIMD Extensions. This is just a code name which Intel uses. But this is the basic history of all the instruction set. So the first set came out in 1999, and right now, currently, 2008, the AVX 512 set of instructions is being supported in Intel. So each of these families adds certain bits. So SSE and AVX differs in the way they emit the assembly, the way the order of the operators are written, the operands are written, and they have certain easier operations. But basically, they expose a 128-bit register, which can parallelly operate on, say, 4 32-bit floats. And I think the AVX2 family introduced 256-bit register, which means you can parallelly operate on 8 32-bit floats. And currently, 512 means you can parallelly operate on 16 floats. And this is plain instruction. This is plain data parallelism that's happening. So this is all the support from the hardware side. So we as software engineers, what is the currently existing support? So these are the usual suspects, C, Fortran, C++. They have great support for this. LLVM also actually supports emitting vector code. And Haskell does have an LLVM backend. But most of my work was not done on LLVM side. It was focused on the native code generator of Haskell. But OK, we'll not talk about Haskell for now. We're just talking about what is vectorization. And APL, another language, this is the one with support. So when I started my thesis, this was the question which I asked. can a pure functional language support vectorization? This is a little bit vague, so I thought I'll add something more to the question. So the question is, can a purely functional language support vectorization, preserving its original syntax and semantics while being as efficient as low-level systems programming languages? So that's a long statement. If I pass it out, it basically means that I want to emit high performance vector code, but at the same time, I don't want to compromise on the declarative syntax of Haskell. So to do that, declarative syntax of any functional language, we need two things. We need a code generator. We make sure that the code generator is capable of emitting vector code. And for the programmer sitting at the higher level, he shouldn't be programming in assembly to do that. He should have a high-level vector programming library, or maybe any other, maybe the language itself supports some vector programming constructs, and you should be able to program with that. So this was the original idea which I had for my thesis. This was, I think, somewhere back in January. So there's a programming language called Nestle, which not a lot of you might have heard of. It's an ML dialect which was developed back in 1990, and it supports something known as nested data parallelism, which actually is not that important, but this means that you can map higher order functions. You can say you have map increment of a list of numbers and you want to parallelize that. So that is flat parallelism. So instead of increment, imagine that you have another higher order function which itself has some parallelism fixed on it. So it has a tree-like structure to the parallelism. So Nestle allows you to flatten that and emit this kind of code. So this was what I wanted to do for my thesis and proceeded along that track. But that stopped within like 2 weeks because there were some disadvantages in this. First of all, the Nestle code was really, really old. It was written in 1990 and not maintained at all. It was written in common list, which I don't think is a disadvantage, but as a personal preference, I like programming in static type languages. The second point, it actually requires a little bit of context to understand what Nestle is, but I'll be digressing if I talk too much about what the flattening transform is. But effectively, Nestle vectorizes everything. It flattens everything. And sometimes, as we will see, that it is not an efficient thing to do. But the other points are more important. Nestle doesn't have a great I/O manager like Haskell has a very highly tuned, powerful I/O manager, and it was incredibly hard to debug. So in GHC, whenever I have any doubts, queries, I can always post in the ISC, and the original developers are associated with this. But Nestle is hardly being maintained. So I scrapped that idea, and I think around February, I asked in the Reddit Haskell that is anybody interested to support vectorization in Haskell. So that's how I started working on GHC. So you all know GHC is the state-of-art optimizing compiler, and this is the general pipeline of GHC. So the entirety of this is not important, but the main point which I'm trying to say is the portions of the code which I worked on, which was mainly the C++ layer and the assembly code that is generated. So this C++ and the bridge in between. And so originally we wanted a low-level code generator to emit vector code and a high-level vector programming library which will allow us to interact. So that's what I worked on, the code generator mostly and the high level of the code. And there were already small bits of pieces of engineering work which I had to do in certain parts of the pipeline, but mostly all of the work was focused on this part and on the high-level library. So there are multiple pieces where I've made the code changes. So the first one, by parser, I don't mean the parser of the language, but GHC actually has a internal parser for emitting the premops. The premops exist in a file, premops.txt.pp. In that, I added some vector instructions and things like that. A lot of it actually existed before for the LLVM code, LLVM backend. So I didn't have to do a lot of work over there. Majority of the work was focused on making sure that the code generator is able to succinctly generate x86 assembly. And yeah, there were some changes in the way the STG to C++ is emitted. So I'll just want to highlight the major changes that I did. Just have the time here. So this was the code change actually. So this is inside the GHC code. This is the path. So originally the format type didn't support this thing. This was one of the main additions. And this format type is used by the pretty printer for printing out the assembly. So this was an addition, vector format. The length is the length of the vector. So if it's 256-bit, say it's 128 bits and you're storing 32 bits, so the length will store that 4. Scalar format will say whether you are operating on floats, doubles, integers, and the width is the actual width of the register. So this was one of the main fundamental code changes. The other things were obviously inside the code generator. So the instructions that you see here, like broadcast, extract, these are actual assembly instructions. And I just highlight these two, but there are a number of other instructions like arithmetic, logical, things like that. And in the C++ interpretation of the machine operations, I made some very few changes. This already supported a lot of that, but there were certain small engineering challenges which are not that relevant, which was done there. So at the end of all of this, what we had was, so let me take an example and show you. Say this is an example of a broadcast operation. This is an assembly operation. So what you're seeing here is a 256-bit register, and the last four things that you see is a 128-bit XMM register. And the thing at the top, the box at the top is a 32-bit register. So what a broadcast is doing is it's broadcasting the same. Say you wrote broadcast 5, it will broadcast 5 to all the four zones here. And then you can do any kind of vector operation. So I'm just taking this as an example and showing you what the code is emitted. Not sure if that's readable, but it mainly just shows the difference between the STG, CMM, and x86 assembly that's emitted. So if you see, there's not any changes in the STG, but the CMM generated by the native code generator now emits something called MOVF broadcast. And 4 is the length of the integer stored, the float stored, and W32 is the width of the float that it's operating on. And this is the assembly that's generated. So there are lots of other instructions which I've elided, but the main point is the V broadcast SS operation. This is an x86 vector operation, which is exactly doing what I said. So at the end of GSOC, what I had was I had float and double working. So float and double could emit. It does emit in my branch, and all of those changes are available. For integer, we have not added SIMD support yet because we had to redefine the way integers were defined. I'll talk to you about it. So the basic user level API, what you as a programmer can do is something like this. So all of these things which you are seeing are a little bit low level. So the float sharp, or float x4 sharp types which you are seeing, these are unlifted types. So you can pack float, you can broadcast it, and once you have like the big vector operators, you can do arithmetic operations like plus, minus, times, divide. There's some things which I didn't include, negate, but that's the general API of what you can show. I'm going to show you an example with that. The change which I made in integers is this. So initially integers were not initial, I mean still is defined like this. So for example, you have int 8, int 16, int 32. All of these are defined in terms of a single machine-dependent type int sharp. So this will be a 64-bit operator in a 64-bit register in a 64-bit machine. For a 32-bit, it would be 32-bit. So now GHC, after all the patches that we have made, the initial patches were worked by Michael Terapeta, and then all of the following ones were done by me. So now int and 8 can be defined in terms of int 8 sharp, int 16 in terms of int 16 sharp, which makes the SIMD operators easier. So now when you are working on, say, 8-bit integers, you can pack those 8 bits into the SIMD registers and things like that. So I'm going to show you an example now, the example code, using the same APIs which I have. So the example which I take is dot product. So what is the code visible at the back? Okay, so imagine you have two lists of floats. What this code is doing is actually just multiplying each of them one by one and then summing it up. So you can see this code. But the problem with this code is that, so I'll just show you that this works. So actually what I'll do is I'll try to compile it with my own machine GHC before working with my branch. So if I say ghc.p.hs, it will say that SIMD vector instructions require the LLVM backend. So instead of that, now I'm going to use my version of GHC, which is the modified branch. And you can see I've added a few new flags, such as SSC4, AVX, dedump. So SSC4 and AVX are the microarchitectures which I showed you, and they are used to emit the code. And I'm actually doing dedump ASM. I'm just going to show you through the assembly code that, yeah, it's actually emitting vector code as well. So if I run that, and I'll show you that this works. So yeah, this works. But the main important part is that it's now actually emitting, as you can see, all the instructions which are prefixed with V, these are vector broadcast, vector move, then even the XOR PS. So anything that is operating on XMM1, XMM0, these are all vector registers. So all of these operations are being done in a vector way. So okay, so the code generator works now, and it is able to do that. But the thing is, we wanted to have a declarative syntax. But this doesn't look declarative, right? I mean, this is a one-line function. So if I had to say, for example, if I wrote a scalar version of this, I mean, so this will just be, this is actually x, say I have x's, y's. This will be zip with, so I'm zipping it here. That's it. So this is the code, which is the scalar code. I'm not sure if it is visible. But this is the code which we originally had. This is the scalar code. And now just for the sake of vectorization, this has become this. So, so the original logic is not at all visible, actually. So just if you look up, there is vec add, vec mul zip, but this is what this code is becoming. So this is not good. We don't like this. So this is spoiling the declarative nature of Haskell. So okay, this is not important. What I did was I started working on another library. This was in the last 1 month. This is not part of GSOC. So this is part of my thesis, where I created a library which I gave this headline, polymorphic SIMD functions for vector programming, which kind of highlights what it does. It gives you some polymorphic functions. So you can see lots of unlifted types, unboxed tuples. My main aim initially was to hide that and make sure that you are able to program through it. So libvector provides you two interfaces to interact with the vector types. One is data primitive, and the other is data.operations. With primitive, it just provides you a lifted version of the unlifted operations. And what operations does, I'm going to show you later. But this is what the primitive module is. This originally exists in this code base, ages called primitive, but that was for the LLVM backend. This is what it looks like right now. For example, if I show you the dot product with so this is the dot product now with all the unlifted types removed using the primitive operators. So what primitive is basically doing, if you are interested to know what primitive is doing, it's basically providing you an associated type called elim and element tuple, which is allowing you to abstract over the low-level things. So right now, say broadcast initially had 4 tuples for floats, 2 tuples for doubles. We have avoided all of that, and all of those heavyweight lifting is being taken down in the instances. And I've also defined num instances for this. So this part makes it look a little bit simpler, but still it's not very declarative. It can be made even simpler, which we shall see onwards. So data.operations is the main module with which I would like people to program in vectors. So as you can see, this exposes the general well-known variants of fold, zip, fmap. And I'll talk about scanb, what that is. That's not important right now. But you will notice that it is a little bit different from the general folds, that the first function, it's taking 2 types of functions. So up till this, if you emit this part, it's just a general fold. For zip, it's a general zip. For map, it's a general map. But what is this additional function that it takes? So the problem is, imagine you are working on a vector container which has, say, 18 elements, and you have a vector of width 4. So you pack it as 4, 4, 4, 4, and 16. So what do you do with the last 2 elements? So the first function is basically for the last 2 scalar elements, where I do a scalar operation, whether it is multiplication, addition, or things like that. I think the API can be simplified, but this is what I could come up with right now. So the containers, so as you can see, there is a type T here as well. T is the 2 types of vector containers which I exposed. So I have vector lists and vector arrays. Vector list is nothing, it's just a plain wrapper over normal lists. But the implementation, the way the instances are defined, those are unique. Those are the things which I'll talk about a little bit later. Vector arrays are just a wrapper over unboxed vectors. And this has a shape polymorphic thing, but I'm not going to talk about that. That's a very common thing which is present in all array libraries. What it does is basically gives you a way to make sure that the arrays that you define, the matrices that you define, those are type safe. But that already exists in Repa, Accelerate, and other array libraries in Haskell. So how are the data? So the new version using this operator, if you want to see what it looks like this. So this is using vector lists. So this still resembles the original one. The only difference is that now we have to pass two operations. So when we are doing multiplication, we still have to pass a scalar multiplication as well as a vector one. But apart from that, it is starting to look like the original scalar dot product. So how are the data operations, the operators defined? So I'm taking each of these individual operations and showing you. So zip is generally just doing a normal zip. So what it does is it splits the list into packs of 4, packs them, and does the multiplication. All of the vector 1, vector 2 that you're seeing, these are XMM, YMM registers, or the vector registers we're doing. The mapping operation is also something similar. It splits the vectors into list of 4 and does all the multiplication and operations like that. Fold is also something similar. It splits whatever operation it has, whether it's an array, whether it's a list, it splits it into parts and then applies the final operation. So the unique thing is scan. So scan or prefix sum, this looks like an inherently sequential operation, right? So for example, say take a scanl of this list. And if you look down, like it looks like a very sequential operation. So the implementation of scan is the tricky part. So there are two types of implementation of scans. So this was the original part of implementation which I did. This is the simpler one to implement, where you can see we start out with unique elements x0 to x7, and by the time we parallelly do this computation, we finally end up with this thing. So you have eventually taken a prefix sum of all of the elements, but done all of that in parallel. But the problem with this scan is that it does O of n log base 2n work. What I mean by that is basically the number of addition operations. If you see, if you did a general scan, you would just add 7 times. But the number of addition operations that it's doing now is actually more than what a sequential version would do. So this is not a work efficient scan. So the scanB operator, which I showed in the type class, that is actually something known as the Blalock scan. So what it does is it's reducing the number of scans, it's reducing the number of addition operations that is done in parallel. So you can see in the previous scan, it was actually doing each of the folding operations twice, but here each of the element is doing them once. And this is the first operation, which is an upsweep operation, and how it implements the scan in this. And then for the remaining operators, the even number element, it does a downsweep where it takes a 0 and it folds it down. So you can see this is the final list that it looks like, and it is the prefix sum of what it originally started with. So if you notice, this algorithm does it in 2 steps, and what you need is this cannot absolutely be implemented using lists, because it bases on the fact that you need mutable arrays. The array should be mutable, and if you are making a copy, you are then spoiling the benefit of doing this operation. So for doing that, we did all of this in the vector array container rather than vector lists. So that's something. So the question is, are scans really that useful? Yes, there are lots of applications of scans. You can see them on the screen. There's polynomial evaluation, radix sort, parallel quick sort, and lots of things like that. So if you're interested in that, then this is a recommended reading for you, Prefix Sums and Their Application by Guy Blalock. So the question is, are folds, maps, zips, and scans, are they enough to implement every algorithm? So maybe. I have not yet found any algorithm which I can't implement. So I had some problems with polynomial evaluation. I could not implement that only using these operators. But for that time, at the time of writing those slides, actually I didn't have scan implemented. So it seems polynomial evaluation can be represented using scan. But there are a number of other algorithms in which you cannot use just these 4 combinators to express yourself. So I'll just see. So there are some good benchmarks which I have. Any of the algorithms where there are heavy reads and less writes, this library tends to perform pretty well. So this is a particular example, such as Pearson correlation coefficient, where you take a number of elements and you are collapsing all of them down to a single value. So you are not creating a new array or a new vector. So this tends to perform better for that. So I'm not sure if that's visible, but yeah, this is the comparison with a general Haskell list. This is how vector array performs, and this is how vector list performs. Surprisingly, vector list perform better, but I have not made any optimizations in vector arrays right now. It can be optimized much faster and made better. Matrix multiplication is a thing where you have heavy writes. Basically, you are recreating the entire array, and that is when actually vector arrays perform worse than vector lists. But that is without me making any optimizations. Before that, it was performing like that. So write performs now better. So I've started using a mutable array, and I'm using the st-monad to do the thawing and freezing and making sure that it's a mutable operation and no copies are being made. You lose a lot of performance whenever the copies are being made. So it tends to perform better now, but I don't have any benchmarks right now with me. So that's almost most of it. So these are the future work which I have thought about, which can be done. So each of these topics individually can be big research topic. Like I tried implementing the SLP algorithm, which is an automatic vectorization algorithm inside GHC, but I didn't face a lot of success, and I didn't have a lot of time to implement that. But automatic vectorization is an area in which GCC or LLVM already have a lot of work done, and we can learn from them, or maybe we can make sure that the code generator, the LLVM code generator performs better, and it can vectorize. Then LLV, we can depend on LLVM to do the vectorization. We need an ideal cost model for vectorization. The cost model becomes very important because at times the packing and unpacking operations, they weigh down the benefit that you get by parallelly operating them. So if you have too many packs and unpacks, then it might weigh more than the sequential version. So we need to have a sane cost model. Mutable arrays are very important. I think in the keynote, Simon was talking about linear types for modeling mutable arrays. And this is a programming language which I started using very recently, Futhark, which is being developed by University of Copenhagen. So they are also using something called uniqueness types to model mutable arrays. That's something from which we can take some inspiration, maybe. Currently, I just support vector lists and vector arrays. We can obviously have more vectorized data structures. The API of libvector, the library, which can be improved, which I showed you, that it now needs a scalar as well as vector version of the function. Maybe we can simplify that. And lastly, the intermediate representations in GHC, we can play with some other intermediate representations because a lot of these automatic vectorization algorithms depend on your language being in the SSA form to actually vectorize. So that's something which might be an experiment worth doing. So if you want to do any follow-up readings on this, any paper by Guy Blalock on this topic is almost a gold mine. So this, I would recommend the first paper the most. Actually, I have myself not read all of them, but Vector Models for Data Parallel Computing is his thesis, where he actually shows how to map vector code to a normal PRAM machine. And from the Haskell side of things, these are the two papers which I read. This is automatic SIMD vectorization in Haskell and the exploiting vector instructions with generalized stream fusion. So if you are lazy and you don't want to read those, I actually have a 5,000-word summary of that. It's present in my repo. I've given you the link. And yeah, that's about it. Haskell is already a great parallel language, and it could become the state of art in vector programming, but that depends on what you mean by state of art, because I have always tried to, whenever I was benchmarking any vector code, I've tried to benchmark it alongside with the C code emitted by LLVM, and it always tends to perform much worse. There were lots of additional moves and loads, and I'm not even sure why those happens. And if I hand load those assembly and remove some of those moves and loads, it became much more simpler. So yeah, maybe we should do some research on that and find out. And lastly, I would like to give special thanks to my GSOC mentor, Carter. He kind of guided me through my code. Graham Hutton was my thesis supervisor, who is in the crowd. And Ben Gamari recently started working on the patch as well. So I think it started working on it a couple of days back, and you can expect that the vectorization patch, the float and double patch at least will land, I hope, in the next 6 months or something. And also Google for funding me as part of the project. And I am looking for a PhD advisor in this field. If there's any academic person in the crowd who's interested in high-performance functional programming, please do get in touch with me. And yeah, thank you for listening. So questions, yeah.
When do you have plans for adding integer word instructions?
Okay, so the question was when do I plan to add integer support? that totally depends on when the int 8 sharp, int 16 sharp, and that patch lands. Actually, int 8 sharp landed, and then Simon was telling me that it broke due to some reason. I think it broke because for the i386 support, the 32-bit processor. I've done all of this code in this machine, and I have not tested for 32-bit machines. So if I can fix that, I hope in the next few cycles, if int 8 sharp, I think if it lands by GHC 8.7, then in the next version, maybe we can start integrating the integer support. It's pretty simple. It's similar to how float and double was. So there is not a lot of work involved in that. Yeah.
Bit of an obvious question, but you did mention wrapper and accelerate. So accelerate in particular generates its own LVMIR and x86 code as well. So how is your approach different from those libraries?
So it's not much different. It's just an integration with GHC, and I wanted to see. So accelerate perhaps doesn't get all the optimizations that are happening after the code generator. So I think accelerate cuts off. I'm not sure. Maybe some person in accelerate can comment, but I'm not sure when accelerate actually emits the code. I don't think it lasts till the STG. So there are certain optimization which happens even after the STG. So even in the code generator, when you have CMM, there are 10 or 15 optimization passes which are happening. So we do gain something from that. So that might be something in which it is superior.
Is this compatible with SPMD transformation? Like the Intel SPMD compiler, which
the ISPC compiler.
Yeah.
Oh yeah. That's a very interesting topic actually, and I wanted to see if I can. So what the ISPC compiler does is it emits. I think it uses GCC itself, right, underneath, or some no. It uses some
the
other.
Intel C compiler is used underneath.
Underneath, yeah. So I'm not sure. I really like that model of SPMD on SIMD, and I wanted to see, but the runtime is totally different, right? Like if you have read the ISPC paper, it has some other constructs like launch and things like that. So those are something I really want to try out. I didn't write in the future work, but yeah, this is something that if the runtime can be coaxed into following that SPMD or SIMD model, that'll be great.
So a few years ago, we had some ideas about how to do this declarative style programming while also getting the performance, like the generalized stream fusion thing, which was done specifically to use vector instructions with the LLVM backend.
Okay.
So have you looked at, and at some point at least that worked, right? I don't know if it still works, but at some point that worked. So have you thought about just trying to port that or enable that same functionality for your backend and
so
seeing
which
how things
approach
work?
were you saying that it worked originally?
The generalized stream fusion thing, right?
Okay,
that like the second paper that you had on the list, like that worked at some point. There was a library, Geoff had a library.
Okay. I have not actually seen that.
Okay.
But I was interested in the data parallel Haskell project in general and wanted to see if that I could make that work. But this had more traction that time from the Haskell community.
No, it wasn't data parallel Haskell. It was something that Geoff Mainland did to a large extent. Just the reason why all these instructions exist for the LVM backend is mostly to enable that thing, right?
Okay.
So now if you add instructions
to tap into the fusion.
Sorry?
So to tap into the fusion, are you talking about?
Yes. So now if you added the same instructions for the native code generator, it would be interesting to see how that works out with that framework.
So absolutely, you're right. And the fusion is a very important thing which I wanted to tap into. So if you saw, I recommend, okay, that's switched up. But anyways, there was a paper which is exploiting vector instructions. So I think Roman was a co-author in that paper. And in that, the performance was actually comparable to handwritten C. But I think that is mostly happening for the fusion that is taking place. So yeah, right now I have no optimizations in place for vector arrays. But yeah, we can add certain rewrite rules and make sure that it can optimize further. Yeah, that's an interesting topic.
I don't really know anything about this stuff, but I was wondering, is there a layer on top of RISC architectures that can make use of vectorization? Or is
Sorry, can you repeat the question?
Is there a layer on top of RISC architectures that you can do to make use of vectorization? Or does it have to be that low level? for it to be useful?
I think it has to be that low level. I think the x86 code generator, it simply emits x86 code. So this was the path which I took. So whatever x86 instructions I could support right now. So currently we have mostly arithmetic operations, packing, unpacking, broadcasting, but there are lots of other x86 instruction sets which are interesting. So that is what I am targeting, and that was the main goal.
Okay.
Are there any plans to implement simplifier passes that are vectorization aware?
Oh, nice. No, I don't have any plans. So I did not do any changes in the simplifier layer. So that is one layer which I didn't touch. Most of the changes were in the code generator and other code generator related optimization. So maybe in the code generator, in the CMM, there are a number of optimization passes which are happening in that layer. But mostly what Roman was talking about, that is something which I think will give better gains if we can write efficient rewrite rules, because in certain cases, even when I was benchmarking with lists, sometimes lists actually has really good performance because it does list fusion as well, and it's very difficult to beat vector or even repa. So the matrix multiplication I showed, which was vectorized and using in-place writes, it was slower than repa, which is sequential. So yeah, I think that's an area I think which we should concentrate on, writing more rewrite rules and making sure that fusion takes place. I think that's all. Thank you.